This is Linked Data Engineering lecture number 2, RDF and RDFS. In this section, we want to talk about RDFS, which is RDF schema, and how to build models to be used in RDF. So, if we look at a knowledge representation like that, here given as a graph representation, what does it really mean? So the point is, you think to know what it means simply because we are using self-speaking identifiers. We call the planet Pluto, Pluto somehow. We call the moon Charon, Charon. And we call Clyde Tombaugh, the discoverer of Pluto, Clyde Tombaugh. So first they are self-speaking, and then of course I've emphasized this fact also by using these very nice pictures. But the point is, a computer who encounters these URIs and encounters this, given for example in Turtle, has no idea what the URI Pluto really means. So what's in there and how does the intended meaning really come through? So let's have a deeper look into that problem. Okay, what does it really mean? We have a standard triple here. We say Charon is the satellite of Pluto. But we could also, of course, use completely different URIs, which are not self-speaking. So here, something which can be uniquely identified via the URI Pluto is connected to something which can be uniquely identified via the URI Charon, the moon. But if you, for example, look at other kind of identifiers, then you would have here something like Q141, which could be connected to Q142 by a property which is called Q144. So you have no idea what it means. You only have, of course, these graph representations, and you see that this thing somehow is connected to another thing. So what we really need is something that gives us more power of semantic expressivity. So we want to express the knowledge that we have, that we connect with the self-speaking names here, at least a bit. We cannot do this in its entirety, but we can at least do something. So we need more semantic expressivity, and for this we use the next layer of the semantic web technology stack, the linked data technology stack, which besides OWL and SCOSP, for example, also contains RDF schema, the schema definition language for the resource description framework. And this is the thing we are talking about now. RDF schema is officially referred to as RDF vocabulary description language, and it's a language to describe or define vocabularies. What do we need in RDF? We need classes and we need properties to say something about something. So we must be able to define a class. So for the definition of classes, we can do this with a vocabulary expression RDFS class, and then as you see here in red, we define the planet to be of type RDFS class, which means planet here then is of type class. Please note that we have all the prefix definitions always in the lower right part of the slide that you need to complement these abbreviated URIs here in Turtle. So we have the planet, which is of type RDFS class. And then, of course, we can also define an instance of that class. And then, for example, we can say the Earth is of type planet. And we know planet is defined to be a class. Quite simple. The same holds for properties. So if I want to define a property, I use the keyword RDF property. So here, watch out, it's not RDFS property, it's RDF property. But don't ask me why. And for a property, you can define further restrictions, which give you, again, more semantic expressivity. You can define among which kind of classes this property is defined. So for example, here I define a celestial body, which is a class, and then I say satellite of should be a property. So satellite of is of type property. And then I can define the domain and the range of that property to be celestial body, of the class celestial body. So that means I say satellite of has the RDFS domain celestial body, and I say satellite of has the RDFS range celestial body, which means then if I have this information about the property satellite of, I can make more sense of a triple which is connected by exactly this property. Because I could say, yeah, if something is connected via that property, then it must be of the following class, which is defined here as a domain and range restriction, as it is called. So this gives us more semantic expressivity, and we know simply more about the facts we are stating here. In RDF, in the RDF model, everything is a resource. So this is, let's say, the top class. Everything is a resource. So an RDFS class is a resource, RDF property is a resource, and then there are several other things. Of course, you can define literals, or you can define something to be a literal, you can define something to be an XML type literal, you can define something to be a data type, you can define something to be a container, and you can define container membership properties. Everything here is a resource. We will see this then clearer in more detail later on. A much more powerful thing that is given to you via RDF schema is the possibility to define hierarchical relationships. Hierarchical relationships among classes as well as among properties. First, let's start with the classes. Here we define, for example, subclasses and superclasses with the RDFS property subclass of. As you see here in blue, this is the RDFS property, and I can define, for example, planet as a class to be a subclass of celestial body. In turtle, simply stated as planet, RDFS subclass of celestial body, period. That's it. What does it mean? It means that each instance that I define to be of type planet is as well of type celestial body, simply because planet is completely contained within the class celestial body, as you see here in this simple set diagram. And for example, if we look at the other example for properties, you can define subproperties and superproperties with the help of the subproperty of keyword that you have here. And then you say, for example, that the property artificial satellite of is a subproperty of satellite of, which means everything which is connected via artificial satellite of likewise is also connected via satellite of. So this is some kind of a specialization. A specialization of satellite of is then artificial satellite of. So this is much more special as a property. So these two means to define hierarchical relationships you have in RDF schema. Let's have a look at the RDFS language model as a whole. We start with a RDFS resource because this is the most general class that is there. We have said everything is a resource. You see here the red arcs always indicate instance relationships, which means here we have an RDFS class, and a class, of course, is a resource. We have an RDFS literal, this is a resource. We have an RDFS data type, this is a resource, as well as the RDF property. But then we can also say property, data type, literal, as well as resource, they all are classes. So therefore, they are instances of the class RDFS class. Of course, this makes it more complicated, but this is the RDFS language model. Then we have lots of properties given here. For example, RDF type is a property, RDFS comment, we haven't heard about that, we will hear about it shortly, is also a property. Then RDFS subclass of, RDFS subproperty of, domain and range, they all are properties. What else do we have? We have subclass relationships. So for example, an XML literal always is also a literal, and a data type, for example, is also always a class. As well as a data type is always a resource, and a property is also a resource, as well as a class is a resource. So these are interesting relationships among the building blocks of the RDFS language. If you want to know more about that in closer detail, simply follow the link I have given you, and then you can see the RDFS language model in its entirety. Okay, there are a few more keywords left that are also available in RDF schema. So One of them, for example, is RDFS also. This is a possibility to define a relation of a resource to another resource, and usually what we have here, of course, are keywords with fixed meaning. So the meaning is fixed, you should use it in that way. And it means these other resources should be explained by a resource with the help of see also. And if it's not only explained, but it's defined, then you can use the RDFS is defined by keyword, which is a subproperty of RDFS see also. And this defines the relation of a resource to its definition. So the definition is either given via a URI, or it can also be given, for example, as a literal. Then you have RDFS comment, and usually, okay, this is some comment to a resource, usually also given as a text string. Or RDFS label, this is very important. If you want to give something a readable name, this is not an idea, this is a name, then you use RDFS label. The fixed meaning of RDFS label is there a name of some resource is stated. And it can be several names. So you can, for example, define many RDFS label relations for a resource and give, for example, the names in different languages. We will encounter that. We will see that. And then there is something, some super property for all the existing container membership properties. So, for example, this RDF sub 1, RDF underscore 2, RDF underscore 3, and so on. This is an RDFS member. So this is a subproperty of exactly this property. So this is given simply for sake of completeness, and simply also because you need these things to define a formal semantics for that. Okay, to round up everything, let's take a look at an example. Here we have an example which combines RDFS and RDF in a huge turtle serialization example. So first, of course, it starts the first 3 lines with prefix definitions, and then we come up first with the class definitions. We define the class planet, and we say planet is a subclass of celestial body. Then we define the class satellite, and we say satellite is also a subclass of celestial body. And then we define artificial satellite, which is also a class, and this is a subclass of satellite. So it's a specialization of satellite. These are the class definitions. Then we come up with the property definitions. In the property definitions, we have a property which we call satellite of, and we define domain and range of that property, which is in both cases celestial body. So now we have defined the so-called terminological knowledge. So if you consider a knowledge base consists of the terminological knowledge, which are the class definitions and property definitions, and the so-called assertional knowledge, which are facts which relate instances with other instances. And this is the part which comes here, the instance definitions. You can also call the upper part T box for terminological knowledge and the lower part A box for assertional knowledge. But this is only a comment on the side. Let's have a look at the instances. We define Earth to be a planet, and then we define Moon to be a satellite, and it's a satellite of Earth. And then we define an artificial satellite, which is called Sputnik 1. So Sputnik 1 is the URI of an artificial satellite. And we say this is also, or has been, a satellite of Earth. And the interesting thing here, we define also now a name for the satellite, because what you see here as the subject is the URI. This is not the name. So if you write this URI in its entirety, it's much longer. It, of course, has some kind of a prefix, and it follows the standards for URIs. It's not a name. You define the name via RDFS label. You see it here in the 3rd line of this definition, RDFS label Sputnik 1, and it's given in English language. And then you give an RDFS comment. For example, you can say, this thing, Sputnik 1, referred to as Sputnik 1, is the first artificial Earth satellite in 1957. You see, defining something in RDFS is quite simple. This is not a lot of semantics which is put in there, but you have hierarchical relationships and you have so-called domain range restrictions. And it's better than nothing. You can do something with it. And what you can do with it, I show you in the next part of the lecture when we talk about possible logical inferences that we can draw based on the formal semantics of RDFS.